Continuing on now to Chapter 6, Section 1. This is the only section we do in Chapter 6, and it'll give you some background in systems of two linear equations and two variables. Now, we have gone earlier to do graphing of a single line. We've also used parabolas and x to the third, in which we get these funny shapes and many other things. But now we're going to get two equations going at the same time. Now, as you may recall, that a particular equation, for instance, this one in red, 2x plus 3y equals 12. And this equation in blue, 3x minus 4y equals 1. Now they are different equations, as you can tell. The x's are different, the y's are different, the constants at the ends are different, and one line starts low and goes up, so this is positive slope. The red line starts high and goes down as it moves to the right. This is negative slope. But a unique thing is happening right at this position here. And you might say, well, what's happening there? Well, the lines are intersecting. And at this particular point, the ordered pair, the x and y coordinates of that point, are a solution for the blue equation and also a solution for the red equation. Wow. And that's that one unique point. Remember, along a line, there's an infinite number of ordered pairs. But here's the one unique point, set of coordinates, that is a solution for both. So if you were to graph these and find that point by their intersection, we would have said you have solved this system of linear equations in two variables simultaneously by graphing. Now, another interesting thing may occur as you look at example B. There's an equation in blue, and there's an equation in blue. Now, if we were to graph both of these equations and they look different, the lines would actually be one on top of another. Because even though there are subtle differences between them, they are the same equation. Now, how many solutions are there then? Well, we said there's an infinite number of solutions along each of the lines, and since the lines are the same, we say there's an infinitely many points, infinitely many solutions for this situation. Now, in a third scenario, letter C, we have the red equation, and we have the blue equation, and when we made a graph of each equation, we notice something about the lines. They are parallel. Now they have the same slope, but you might notice they have different y-intercepts. Y-intercepts, that is, where they cross the y-axis. When lines are like this, there's never going to be a common point of intersection. So we say there are no solutions. So these are the three scenarios we're going to be looking at in Section 1 of Chapter 6, and hopefully you're going to have these in your notes. Now, if we actually made graphs of those sets of equations, we would have used the graphing method to solve them simultaneously. But there's also algebraic methods for solving them. And we're going to look at this first example using what is called the substitution method. Now, what is this? Well, as we look at these two equations, these are both in what we call standard form. AX plus BY equals C. You may recall that from an earlier lesson. They're both in standard form. Now, when we notice that in one of the equations you have just the letter Y there without a coefficient other than 1, there's a 1 there that we don't write. If we solve this equation for the letter Y, and we can do so by just taking that negative Y, bring it over to the other side, it becomes a positive Y through transposition, and we take this 1 that's on the right, bring it over to the left as a negative 1, we now have that Y is this. And by the way, when it's in this form, Y equals mx plus b, this is slope-intercept, where m was the slope, or is the slope, and b is that y-intercept, where it goes through the y-axis. So, we're now going to take this value of y and put it in the other equation. So let's do that. So we have 3x plus, now it's 2y, so I'm going to put the 2 there, but now I have this value for y, which is 2x minus 1, and now that's going to equal 4. Now, in review of what we've done so far, they were in standard form. We solved one of the equations for the letter y. So now we have a value for y. We take that value and substitute it in the other equation where the y is. And now we're going to distribute. And notice we also have an equation with only one kind of letter, x. So 3x plus 4y, 4x, it's on a real row there, and then minus 2 equals 4. So now we combine like terms, and we get 7x. We're going to transpose the negative 2 to this side, becomes a positive 2, and we get 6. 2 plus 4 is 6. We now solve for x, and we get that x is 6/7. And we can see that there a little bit too. If we brought that down, that's what it is. So now that we know one letter, we now solve for the other letter. Again, our x value was 6/7. So we're going to substitute that. 2 times 6/7 minus y equals 1. So here we get 12/7. I'm going to bring this 1 over as a positive 1, but I'm going to put it in the form of, well, actually a negative. When this 1 comes over, it's a negative 1. But I'm going to put that 1 in the form of 7/7 so I can actually combine these terms. And I'm bringing this negative y over to this side as a positive y. So I now end up with 12 minus 7, which is 5/7, and that's what y equals. Now I have an ordered pair. You may recall our x was 6/7, and our y is 5/7. And I was able to solve this through the system of substitution, where I solved for y, then substituted that value into the other equation, multiplying through, getting a value for x. Then once I had a value for x, 6/7, substituted it here, and then solved it. And I did it slightly different, but there are different ways to do it. And if you had a graphing calculator, you could put it in as two equations, and you could actually see the point of intersection. But notice it would be hard to pick out fractional values for your x and y. If they're whole numbers, that's rather easy. Okay, now there's another algebraic method that can be used, and we're going to take a look at that one right now. It's called the Elimination Method. Now let me set that up for you. The elimination method starts off in a similar way. That is, you put them in standard form. But now you're looking to see, if you were to add these together, would one of the terms as a set be eliminated, that is, subtract out? And you might say, well, there's nothing here that would do that. But we are allowed to modify equations. And we're going to modify this first equation by multiplying every term by something, so that eventually something would cancel out. Now notice, if this were a negative 2y, and I were to add these up, the y's would cancel out. So I'm going to multiply this, and I kind of ran out of room here, by a negative 2. So a negative 2, I'm going to multiply each term by that. This is I'm going to do it down here because I don't have any room. A negative 10x. Negative 2 times positive y is a negative 2y. I usually like to put it right to the side so you can see what you've done. And then negative 2 times 4, a negative 8. Now notice I don't have to modify this one in any way. I just will copy it down just as it was. So this is going to be 3x plus 2y equals 1. Now notice, if I put a line underneath these and add them up, this then becomes a negative 7x. Here, a negative 2y and a positive 2y, they just cancel out, and that would be a 0. I don't write that. And this, when I add these up, it's a negative 7. So I have negative 7x equals negative 7. I'm going to divide both sides by a negative 7. And I get x equals a positive 1, just as they have here. So reviewing what we've done, they're in standard form. Nothing will cancel out this way. But if I multiply this top equation, and I do this by looking at it and studying it a little bit, judging, making decisions. If this were a negative 2y here, they would cancel out. So I multiply this by a negative 2, which is what I've done over there. And then I get this new equation. Now, when I put my line underneath them and add them up, I finally get x equals 1. So I have one value. So I take my value of x, which was a 1, put it in either of the equations. I get 5 times 1 is 5. I'm going to transpose that 5 now to the other side, where it becomes a negative 5. A negative 5 and a positive 4 gives me a negative 1. So y equals negative 1. So my ordered pair then was 1 for x, a negative 1 for y. And this is a unique solution that I could place in either of the equations and have it be true. All right. So let's take a look at number 3 now. So I may not have been recording. Let me just review this one more time. Example 3. 2 equations in standard form. If I were to draw a line under them, nothing would cancel out. But I'm allowed to modify these equations, both of them now, so that something will cancel out. I've chose to modify the y's. So I'm going to multiply the top equation by 3, the bottom equation by 4. I get this. Now my y's cancel out, and I get 17x equals 51. Divide both sides by 17, x equals 3. Now when they did it, they ended up with getting rid of the x's first. You can do that as well. They got y equals 2. Well, I had x equals 3. I had to prove that y equals 2. Well, I took my value for x, put it in this equation up here, solved it, and I get that y equals 2. So there's my ordered pair. Now, recalling as we introduced section 1 of chapter 6, we said there were 3 possibilities. They would intersect in one place, and that's what we've been doing so far. We could do it by graphing, by substitution, or elimination. We've shown that. Or if you were to graph them, it could be the same line, just disguised. Or if you were to graph them, they would be parallel lines. These would never intersect. Well, this is what we're going to talk about here. Dependent systems are in which the equations look different, but they actually are the same line. So there's an infinite number of solutions. How do you find that other than graphing? Well, we're going to show you. We can use both of these methods, substitution and elimination. And then we also have those that are what we call inconsistent systems, where the lines are parallel and they're never going to intersect. So how do we do that? Well, take these 2 equations here. Do they look like they're the same? And the answer is no. But if they're both in standard form, if you were to put them in slope-intercept form by solving for y equals mx plus b, and then you were to compare the slopes and compare your y-intercepts, if they were the same slope and the same y-intercept, they're the same equation, even though they were disguised a little bit. So let's solve both of these for the letter y. And here we get this equation. And solving this for the letter y, we get this equation. And what do you notice about these? They are the same equation. The slopes are the same, and the y-intercepts are the same. So what's the answer then? Well, since they're the same line, we say there's an infinite number of solutions, and we usually give this in what we call set builder equation, set builder notation, where you take one of them, I say the first one, x comma y is such that, that's what that vertical line means, and then you just write out one of the equations, negative 4x plus y equals 2. Now, the second equation could have been used here, and we could actually modify this to make it this. So it doesn't make a difference which one you use. In fact, your math lab will often give you three choices. The first choice would be there's one solution. Second choice, no solution. And third choice, infinite number of solutions. And you just have to pick off which one you want. And if it has a single solution, of course you have to put the ordered pair in. Don't forget to put a comma, not a period, separating them. Okay. Now, one way to do it was the way we just showed you, that put them in slope-intercept form. But if you put it in standard form and went to modify so something would cancel out, you'd see that everything would cancel out. This would be 0, this would be 0, and this would be 0. You'd end up with 0 equals 0. This indicated they were the same equations. Now we describe those equations as being dependent. Okay? Alright, let's go on to example. Now in example 5, again the equations are in standard form. Notice that nothing cancels out here. But if we multiplied this top equation by a 2, this would then become, this is the way I like you to put it in your homework log there and in your notebook there. This is going to be 6x minus 4y equals 8. And then the bottom one we don't change, just negative 6x plus 4y equals 7. So when you go to add these up, this cancels out, but we end up with, on this side, that is 0. Add these together, we get 15. Now that's not a true statement. Remember in the previous example we had 0 equals 0. That's a true statement. Sometimes you might end up with 5 equals 5. That's a true statement. But when you end up with a not true statement, 0 equals 15, this indicates that the equations were of parallel lines. See, this part's the same in a sense. This part is different. So it's the same slope, but different y-intercepts. We also say that these equations are inconsistent. That is, there are no solutions. All right, we're going to take a look now at a few applications. Now, step 1 for any word problem is to read it over, as we've been doing. 800 people attend a basketball game. So 800 is an important number here. And the total ticket sales were this. If adult tickets are $6 and student tickets are $3, how many adults and how many students attended the game? Well, here we're allowed to use two variables, and we're going to use A for the number of adults that attended the game, and we're going to use the letter S for the number of students that attended the game. And we know the combination of these two was 800. That was the total number attending the game. Now we also know how much money was taken in, and we know the price of an adult ticket was $6, and the price of a student ticket was $3, and the total amount taken in was $3,102. So there are my two equations, and they show you how they did it here too. They're using X and Y. I like the idea of an A and an S. Helps you identify. So how do we go about solving? Well, we could use the substitution method where we can say S equals 800 and then just transpose the A minus A. Or we could modify this top equation by multiplying everything by a what? If I want to get, let's say, the 3's out of there, or the S's. I gave that away a little bit. And the answer would be a negative 3. Don't have a lot of room. So let me write that underneath here. So this will be a negative 3A. This will be a negative 3S. I'm multiplying a negative 3 by each of these terms. And this will be a negative 2400. So I put my line. Now I'm going to eliminate the S's. And here I get 3A equals, well, I had to get my calculator out, so I subtracted 2400 now from 3102, got 702, and then I divided both sides by 3. I get A equals 234. Well, if that's the number of adults, plus the students are going to be 800, I'm now going to subtract or transpose this, and I get the number of students as 566. So again, they're going to show us the textbook, how they did it. I wanted you to see it done in action. And there we see it. So the use of systems of linear equations to solve variables in which there are two variables simultaneously through graphing, substitution, elimination, setting up your word problems, and of course you'll have practice as we do our homework. All right.